124 light-years away, a planet called K2-18b is giving astronomers one of the clearest looks yet at the atmosphere of a distant sub-Neptune. JWST has detected methane there, and newer observations strongly support carbon dioxide as well. But beneath that hydrogen-rich atmosphere, scientists still do not know what kind of world K2-18b really is. A deep ocean? A massive gaseous interior? Or something even hotter beneath the clouds? This is what the evidence actually tells us about K2-18b. K2-18b orbits a cool red dwarf star in the constellation Leo, roughly 124 light-years from Earth. It is not another Earth. The planet is about 2.6 times Earth's radius and roughly 8.6 times its mass. Its relatively low density tells astronomers that K2-18b contains much more volatile material, gases, water, or both, than a rocky planet like ours. Scientists classify it as a sub-Neptune. These worlds are common throughout the galaxy, but our own solar system contains nothing quite like them. K2-18b circles its star every 32.9 days and lies within the star's conventional habitable zone. But that phrase can be misleading. Being in the habitable zone does not mean a planet is habitable. It simply means the amount of energy received from the star could, under some atmospheric conditions, permit liquid water. K2-18b is far larger than Earth and surrounded by a hydrogen-rich atmosphere, so conditions beneath those clouds could be radically different from anything on our planet. K2-18b was first identified in 2015 using NASA's K2 mission, the extended mission of the Kepler Space Telescope. Later observations refined its mass, radius, and orbit. Then, in 2019, observations from the Hubble Space Telescope produced an absorption feature initially interpreted as water vapor. That result attracted enormous attention because the planet lies in the habitable zone. But Hubble covered only a limited region of the infrared spectrum. Water and methane can produce overlapping features there, and later studies showed that methane could explain much of the signal originally attributed to water. To investigate the atmosphere properly, astronomers needed a telescope with far greater infrared capability. They got one with the James Webb Space Telescope. In 2023, JWST watched K2-18b pass in front of its star. As starlight filtered through the planet's atmosphere, different molecules absorbed specific wavelengths. By measuring those tiny changes in the light, astronomers could begin reconstructing the atmosphere of a planet more than 100 light-years away. The strongest result was methane. Methane was detected at high confidence, and that detection has survived subsequent independent analyses. NASA Science. The original JWST study also reported carbon dioxide. Later reanalyses disagreed about how secure that signal was, but 4 newer JWST NIR spec transits produced a high-precision spectrum that robustly detected both methane and carbon dioxide. Those newer observations also strongly support the conclusion that K2-18b is water-rich. But that requires an important distinction. A water-rich planet is not necessarily an ocean world. One possible interpretation is that K2-18b has a relatively thin, hydrogen-rich atmosphere sitting above an enormous liquid water ocean. This is known as the Heysian hypothesis, from the words hydrogen and ocean. K2-18b has become one of the best-known candidates for this proposed class of world. But no telescope has directly detected an ocean on K2-18b. The same observations can also be explained by a much thicker envelope containing large amounts of water mixed deep inside the planet. Water there could exist as vapor, high-pressure ice, or supercritical fluid rather than as an Earth-like ocean. Other researchers have modeled K2-18b as a gas-rich sub-Neptune with no habitable surface at all, while another interpretation allows for a magma ocean beneath the atmosphere. And the thickness of the hydrogen atmosphere is critical. Too much hydrogen could produce an intense greenhouse effect, raising temperatures and pressures beneath the atmosphere far beyond conditions suitable for liquid water. So K2-18b may be water-rich, but whether any of that water forms a temperate liquid ocean remains unknown. Then came the part of the K2-18b story that generated the biggest headlines. Dimethyl sulfide, DMS. On Earth, much of the DMS found in our atmosphere is associated with biological activity, particularly marine microorganisms. That makes it interesting as a potential biosignature gas. But a potential biosignature is not evidence of life unless two much harder questions can first be answered. Is the molecule really present? And if it is, can non-biological chemistry produce it? The first JWST observations in 2023 contained only a tentative hint of DMS. Then, in April 2025, researchers using JWST's MIRI instrument reported mid-infrared features consistent with DMS and a related molecule called dimethyl disulfide, or DMDS. The signal was reported at roughly 3 sigma significance. That was interesting enough to investigate, but it was not a confirmed detection. And independent teams did exactly what science requires. They tested it. Researchers reprocessed the observations using different analysis pipelines, different atmospheric models, and broader selections of possible molecules. A joint analysis combining JWST's NIRISS, NIRSPEC, and MIRI observations found insufficient evidence for either DMS or DMDS. Other molecules could reproduce the same spectral features, and small differences in data processing changed which interpretation appeared preferable. Another statistical study found that most reasonable retrieval configurations did not favor DMS or DMDS. And the newer NIR-SPEC observations that strongly detected methane and carbon dioxide found only marginal signals for DMS and related molecules, none reaching the level required for a secure identification. So the evidence today is clear about what we can and cannot say. Methane is securely detected. Carbon dioxide now has strong support from newer JWST observations. K2-18b is strongly supported as a water-rich sub-Neptune, but DMS and DMDS have not been securely detected. There is no confirmed biosignature, and there is no evidence that life has been discovered on K2-18b. The biggest mystery surrounding K2-18b is therefore more fundamental than life. What actually exists beneath its atmosphere? A vast liquid water ocean? A deep envelope of hot compressed water? A gas-rich interior with no distinct surface? Or perhaps a magma ocean beneath the hydrogen-rich sky? Right now, several of those possibilities remain compatible with the observations. That may sound less dramatic than announcing an inhabited ocean world, but scientifically it is far more interesting. Sub-Neptunes are among the most common types of planets discovered around other stars, yet our solar system has no example of one. K2-18b is giving astronomers a rare opportunity to understand what these worlds are actually made of, and whether some of them can maintain liquid water under conditions completely unlike Earth. JWST has already transformed what we know about this planet. It has given us strong evidence for methane, carbon dioxide, and a water-rich interior, while also showing just how difficult it is to identify individual molecules in the atmosphere of a world 124 light-years away. And the DMS debate demonstrates something equally important. Science does not end when an exciting result is announced. Other researchers test it, challenge it, reprocess the data, gather more observations, and change the conclusion when the evidence demands it. For now, K2-18b remains a temperate sub-Neptune with an atmosphere we are beginning to understand, and an interior we still cannot see. Whether there is an ocean beneath those clouds remains unanswered. But the facts we have already uncovered make K2-18b remarkable without needing anything more. If you enjoyed this evidence-based journey to K2-18b, subscribe to Mellori Explores the Cosmos for more fact-based explorations of the universe. And until next time, keep looking up. There is always more to discover.